The next is a crystal lattice. As I said that in a crystalline solid, all the particles are arranged in a definite order and hence they have a definite shape. So now the next part of the chapter actually contains, the next part of the chapter actually deals with the shapes of the arrangement of those particles, that how those particles are arranged. From the beginning of the chapter, I'm saying that the particle, once I'm using a word particle, it means it may be atom, it may be molecule, or it may be ions, depending on it's a which type of particle, it's a which type of crystalline solid. If the crystalline solid is a molecular, we had learned that there are the 4 types of crystalline solid: molecular, covalent, ionic, and metallic. If it is a ionic or metallic solid, then the particle is going to be ions. In case of ionic solid, we have 2 types of particle, that is a cation and an ions. In case of metallic solid, we have there is only 1 type of ions, that is a cation. If it is a molecular solid, the particle is going to be molecule, and if it is a covalent solid, then the particle is going to be the atoms. Okay, so the crystal lattice or space lattice. Now what is crystal lattice or space lattice? As I said here, I just suppose I have a solid and I just wanted to know the shape of or the arrangement of that particle. So all the particles present in a solid, they all are spherical in a shape. Whether it is an atom, molecule, or ions, we consider that the particles are spherical in shape, and those particles are placed properly in some definite order. And when we start drawing the same order, or we represent the same order on a 2-dimensional paper, then it is called as crystal lattice. So what is crystal lattice? Crystal lattice, it is nothing but the diagram, a 3-dimensional diagram. I'm using the word 3-dimensional because if you want to actually represent the structure, then solid is a 3-dimensional. So if you want to represent the arrangement of the particle in a solid, then you have to draw a 3-dimensional diagram. So it's nothing but the 3-dimensional diagram which represent the arrangement of a particle in a solid. That is the way the particles are arranged in a crystalline solid. In the same manner, we draw the diagram. We draw the 3-dimensional diagram which represent the structure or the arrangement of a particle. In this animation, you can see that here we have this animation. It have it's nothing but the crystal lattice of a particular solid, in which those dots, the 2 things are present throughout the structure. You can say that the dots and the lines. Here the dots which are present, those dots are nothing but the these dots are nothing but the particles which represent the position of particles. So dots are particles, and the lines which are present between those dots, those lines are not representing the bond or attraction or something. The bond is nothing but the attraction, and the attraction is not visible. So these lines are drawn only to understand the geometry of the molecules, or only to understand the arrangement of the particle. Suppose in the diagram or in this part, if there is a no line, and if there is a no line, then I can simply say that if no line is there, it means if there is only particle, only dots are there, then simply you cannot predict the structure of a molecule or the arrangement of a particle. So these lines are drawn only to understand the arrangement of a particle. Now the question arises, now in this case you can see in this diagram that all the crystalline solid, since we are talking about the crystalline solid, so whatever the particles we are having, they all are arranged in a definite manner. Their arrangement is fixed. And throughout the structure or throughout the diagram, the arrangement is same. Now, how to draw a crystalline solid? Now to understand that, let's see the another diagram. Now suppose there is in a crystalline solid, as I said, we consider that solid is made up of particles which are spherical in shape. Spherical, that is a ball-like shape. So here you can see that there is a 1 layer of a ball, then 2nd layer, then 3rd layer, then 4th layer, and so on. So we are having a particular, after joining those all rows, we get a particular layer. So in a solid, there is a first layer of the sphere, above which again there will be a 2nd layer of the sphere. So now in the diagram again you can say that on first layer we had just drawn the 2nd layer of the sphere. So after that 2nd layer there is a 3rd sphere, 4th sphere, and so on. So I can say that there is an infinite number of layers of a spheres are present, and the arrangement of a particle in a layer is same. Now I just wanted to draw the crystal lattice. Now how to draw a crystal lattice? I will simply say that for drawing a crystal lattice you consider any 2 layers. any two layers in this, you can say that all the balls are joining to each other, top from the balls present in the same layer or the balls present from the different layer, all are touching to each other. So you start joining those balls which are, or those spheres which are directly in a contact with each other. Start joining the centers of those particles. First I'm joining the centers of the particle from the first layer. Then I'm joining the centers of a particle from the second layer, and since the particle present on the first layer and the second layer are also touching to each other, so I'm joining the particles of the particles from the two different layer. And after joining all these particles, you can observe that here I'm getting a cube. Similarly, when the same thing is repeated, again join the next balls and the particle from this, the next and next, you will get the same diagram which you observe in the first animation, that is in the first one. So here I can say that from at least from this animation we come to know that when we draw a crystal lattice, in a crystal lattice, actual crystal lattice, we represent a particles from a dot, and the line which is plotted is much larger than those dots. But in an actual crystal lattice, the balls are very big in size, and those lines are nothing but the internuclear distance, that is a distance between those spheres, that is between those dots. So this actual diagram is something like this, where the balls are bigger in size and those lines are smaller in size. But here the drawing such a diagram every time is not possible with such a big balls, and the arrangement becomes complicated. So just for the convenience of the diagram, here we represent the spheres by just a dot, and the lines and the internuclear distance, that is the line which we are joining the centers of the nucleus, the centers of the particles, they are represented by a large line, just for the convenience of the diagram. Now when I'm talking about the crystal lattice, there are the certain points or certain terms, out of which the first one is called as a unit cell. Now what is unit cell? In a crystal lattice, you can observe that there is a large number of the same arrangement is repeating throughout. And if I'm asking that which arrangement repeated again and again to get the complete crystal lattice, then which arrangement is repeating throughout the crystal lattice, then I can say that in a diagram, the cubic arrangement is repeating throughout the crystal lattice, and so that it is the smallest unit which repeats throughout the crystal lattice is called as unit cell. So it's called unit cell. So unit cell is nothing but the smallest unit which repeats over and over to produce complete crystal lattice. So this diagram, you can say that this diagram is made up of a large number of the cubes, and each cubes are called as any cube you consider is called as a unit cell. After unit cell, we have a one point called as a lattice point. Now what is lattice point? Now in a crystal lattice, the position of a particle is represented by, in this diagram we had represented the position of a particle by the dots, and the dots are nothing but called as a lattice point. What is lattice point? Then the definition says that it is a point in a crystal lattice which represent the position of a particle. So the point which represent the position of a particle is called as a lattice point. So this whole diagram is called as a crystal lattice, that is which shows the representation of the particles in a solid. And then unit cell, that is any smallest unit you consider, that is any smallest cube you consider, is called a unit cell, and all the dots which are present here is called as a lattice point. Okay, now the next is the parameters of a unit cell. Now I'm drawing a unit cell here. So this is the symbol unit cell. These are the particles which are present on it. Now in the case of this, there are, in this unit cell, I can say that there are the total 6 In this unit cell, I can say that there are total 6 sides, there are total 12 sides, and there are total 8 corners. You consider any one corner to get the parameter of a unit cell. You consider any one corner, any one. Suppose I am considering this corner. At a single corner, you will come to know that the 3 sides and the 3 angles are forming. At each corner, the same thing is happening. So you just measure here. The parameter means we measure the length and the angles, the length of the edges and the angle between those edges. So instead of measuring the sides of all 12, that is instead of measuring all 12 sides, the length of all 12 sides, or at each corner there are 3 angles are forming, that is there are total 8 corners, so total angles will be 24. So instead of measuring 12 sides and 24 angle, we consider any one point, any one corner. Here we have 3 sides and 3 angles. So we just measure these 3 sides and these 3 angles. If these 3 sides are equal, I will say the all the sides present at each corners are going to be equal. That means all the sides will be equal. So similarly we measure each angles, these 3 angles. So here these 3 sides are, that I'm going to this point. So A, B and C. The angles are, angle opposite to A is alpha, angle opposite to B is beta, and angle opposite to C is gamma. So here we are representing the sides by A, B and C, and the angles we are representing it by the alpha, beta and gamma. So we have 3 parameters, 3 sides A, B and C, and 3 angles alpha, beta and gamma. So these are the parameters of the unit cell. As I said, if you wanted to know whether all sides are equal or not, simply you just measure A, B and C, any one corner. If A, B, C are equal, all the sides will be equal. If suppose A and B is equal and C is not equal, then at each corner the 2 sides will be equal and the third side will be not equal. Similarly, I can say for the angle, suppose if 3 angles are there, alpha, beta and gamma, I come to know that alpha, beta and gamma all are equal to 90 degree. Then I can say with the guarantee that all the angles present at each corner is going to be a 90 degree. But suppose only alpha and beta is a 90 and gamma is not 90 degree, then at each corner out of 3 angle, the 2 angle is going to be a 90 degree and the third angle is not going to be a 90 degree. So this is about the parameter of unit cell. Crystal lattice, once again, that is a 3-dimensional figure which represent the arrangement of a particle in a crystal, in a solid or crystalline substance. After that, we have a unit cell, the smallest unit, which keeps on repeating again and again to produce the complete crystal is called as a unit cell. Lattice point, it is a point in a crystal lattice which represents the position of a particle, and this is about the parameter of a unit cell. On the basis of this parameter, we divide the unit cells into the 7 categories. So next we are going to learn about these 7 types of the unit cell depending on the parameters of unit cells.